Welcome back once again in our numerical solving on pipelining series, and today we'll be discussing one more numerical related to our pipelining topic. So the question is, consider the pipeline processor with the following four stages. We are having stages: instruction fetch, instruction decode, and operand fetch. Basically two micro instructions are implemented in ID stage, and then execute stage. In this ALU will perform the operation, then we will talk about the write back. The results will be written back to the memory. So the EFID and WB stages take 1 cycles. They have given, then these stages requires 1 clock cycle, EF, ID and WB. So these stages are required only 1 clock cycle, and the number of clock cycles for the execution stage depend upon the instruction. So they are saying that number of cycles in execution phase depends upon the type of the instruction. If the type is add or sub instruction, needed only 1 clock cycle. If the instruction is addition or subtraction in execution phase, we need only 1 clock cycle. And if we are having a multiply instruction, then the execution phase required 3 clock cycle in execution state. So I think it will be clear, very clear. Operand forwarding is used in the pipeline processor. What is the number of clock cycles taken to complete the following sequence of the instructions? So we are given with the 3 instructions. Suppose this instruction is I1 instruction, this is I2 instruction, and this is I3 instruction. So if we talk about the I1 instruction, it will take 1 cycle in fetch, 1 cycle in decode, and operand fetch, 1 cycle in execution, and 1 cycle in write back. So number of cycles required will be 4 for the I1. For I2, one cycle will be required for instruction fetch, 1 will be required for ID fetch, and 3 will be required for execution phase, because this is the multiply instruction, and for multiply instruction the execution phase stage required 3 clock cycles. So 3 clocks will be required in execution state, and again in write back we will be requiring only 1 clock. In the similar way, for for the subtraction instruction, we will be requiring one cycle for fetch, 1 cycle for decode, 1 cycle for execute, and 1 cycle for write back. So this is the question given. So now we have to find out number of clock cycles taken to complete the following sequence. So as we discussed previously, when we have to calculate the number of clock cycles, then we will be drawing the phase. So let's discuss how we will calculate the number of clock cycles. So as we have discussed in our previous numerical, that we have to write the stages in the column, and we will write the cycles or the clocks in rows. So these are the clocks, actually 1 2 3 4 5 up to 8 clocks. We can add more clocks depending upon the requirement. So what we will do, uh, we will try to start, as I have told, that instruction I1 require, we can draw the diagram in which we will be having phases and number of clocks required. So for the I1, if we say that in if state, then ID stays, then X state, and then WB state. We already talked about in our previous slide all these things, that I1 required 1 clock in if phase, 1 clock in ID phase, 1 clock in execution phase, and 1 clock in write back phase. I2 requires 1 clock in if phase, 1 clock in ID phase, 3 clocks in X phase, and 1 clock in write back phase. I3 requires 1 clock in if phase, 1 in ID phase, 1 in X phase, and 1 in W phase. As we know that I1 is a add instruction, then uh, I2 is a multiply instruction and I3 is a subtraction instruction. So in this phase time diagram, what we will do, at the first clock I1 will come into the pipeline, and after one clock I1 will be completed and it will be moved to the ID phase because it requires only one clock. And at the same time in clock 2 EF phase will be free, so we can run instruction I2 in its EF phase. So after the completion of the second clock, I1 will move to the third X phase, yeah, or we can say that execute phase. And after in third clock, what will happen? I2 will move to its ID phase because ID phase is free in third clock. And as if phase is free, we can put the next instruction, that is I3, into the if in its if phase. Then again at the fourth clock, I1 will come out. Then at the fourth clock, after completion, I2 will come out, and in fourth clock I3 will be completing its EF phase and it will come out into the ID phase. So after this, we know that I2 requires 3 clocks. I2 requires 3 clocks in its execution phase. So after completing 3 clocks, it will move to its write back phase. And because execution phase will be free, I3 will execute in the clock number 7, and I2 will come out of after this phase, and I3 will move to the its write back stage in 8th clock, and after 8th clock I3 will come out. So I3 will come out in 8th clock, I2 will come out in 7th clock, and I1 will come out after 4th clock. So we can see that all these three instructions came out of the pipeline in 8th clock. So number of the clock cycle required to execute the instruction is 8th clock. Thank you. Let's discuss this numerical. In this numerical, they have given, consider the following procedure. Assume that the pipeline registers have zero latency. Means the registers which are used in pipeline design have zero latency, means they don't incur any type of circuit delay. So they are given with the 4 procedures, and all stage delay of these procedures, and they are asking that what will be the highest peak clock frequency. So first of all, see that the procedure P1 has stage latencies. In stage 1 it requires 1 nanosecond, then in stage 2 it requires 2 nanoseconds, in stage 3 it requires 3 nanoseconds, and in stage 4 it requires 1 nanosecond. So we have already discussed it that in different stages the combinational circuits which are used to execute the micro instructions need different times. So we have discussed in our previous examples also. We are given with the stages and having we had been having different type of delays in those stages also. So in the similar fashion, in this numerical they have given a P1 procedure which has these type of delays in different stages. In the similar way they have given a P2 procedure in which the stage delays are given as follow as this 1 nanosecond, 1.5 nanosecond, 1.5 nanosecond, and 1.5 nanosecond. In P3 they said that there is a five stage pipeline, and in 5-stage pipeline they have given the delays. In P4 they have given the delays. It is also a 5-stage pipeline. So what we have to do? We have to find out the uh, clock time actually. If we find out the clock time, then we know that the frequency is equal to 1 by time period. So if we are having the time period of the clock, then definitely we will be able to calculate the frequency of the clock. and they have asked that we are having these four procedures, in which procedure we will get the highest peak clock frequency. So I think it is easy if we find the clock time in each procedure. So what will be the clock time in this procedure? If we say, it will be, what we will do, how we calculate if we are having non-uniform clock delays in stages, then what we will do, we just find out the maximum of these clocks and add it with the registered delay to find the clock time. So in these delays, the maximum is 2 nanosecond. So 2 nanosecond will be the clock time for this pipeline. And as in the numerical, we are given with that we are having 0 nanosecond register latency. So if we add these together, we will get 2 nanosecond. So for the P1 procedure, the clock time is 2 nanosecond. In the similar fashion, for P2 we can calculate, for P3 we can calculate, and for P5 we can calculate. Thank you for listening carefully, and I hope that you people have got some depth into the pipelining concepts. Thank you.